Now let's make note of one. The argument used in the previous example, or example 2, to justify the absolute minimum is a variant of the first derivative test, which applies only to local maximum or minimum values, and is stated here for future reference. Recall that the first derivative test for absolute extreme values. Suppose that c is a critical number of a continuous function f, defined on an interval. For a, if the first derivative, or f prime of x, is greater than 0 for all values of x being less than 0, and the first derivative is less than 0 for all x that's greater than c, then f of c is the absolute maximum value of f. B, if f prime of x is less than 0, or the first derivative is less than 0 for all x which is less than c, and the first derivative is greater than 0 for all x is greater than c, then f of c is the absolute minimum value of f. Now, let's make note of 2. Now, an alternative method for solving optimization problems is to use implicit differentiation. So let's take a look at example 2 again to illustrate this method, and we work with the same equations. So remember that we had the area, which was equal to 2 pi r squared plus 2 pi r h. And we knew that pi r squared h was equal to 1,000, which is the volume, right? So we knew the volume was going to equal 1,000 cubic centimeters. But instead of eliminating the h, okay, what we can do is we can differentiate both equations implicitly with respect to r. So we're going to name the first equation here, and this is the second equation. So let's solve the first one implicitly. So if we want to find a prime, we know the derivative of 2 pi r squared is going to be 4 pi r. Plus, now we're going to have to use the product rule implicitly according to h. Well, the derivative with respect to r is going to be 2 pi h. And then the derivative with respect to h is now going to be, again, implicitly 2 pi r h prime. Okay? And then let's take a look at the second equation. If we wanted to then take the derivative of that one, okay? Well, if we take the derivative with respect to r, then we're going to get 2 pi r and then h. And then when we take the derivative with respect to h, well, this is going to give us pi r squared h, and the derivative of 1,000 is equal to 0. And so that should be h prime there, since we just solved that implicitly. Okay, so now we can see that the minimum occurs at a critical number. So we're going to set the derivative equal to 0 and then simplify. So looking at the first equation, we're going to let a prime, which we're going to set this equal to 0. So we have 4 pi r plus 2 pi h plus 2 pi r h prime. And we're going to set that equal to 0. Now, out of all three terms, we can factor out a 2 pi. And what's left is 2r plus h plus r h prime, and that's equal to 0. And if we divide both sides by 2 pi, then we end up with 2r plus h plus r h prime, which is equal to 0. Okay, now we're going to use the second one. So we have 2 pi r h plus pi r squared h prime and set that equal to 0. So can we factor out something that they have in common? Well, they have a pi and an r in common. So we end up having 2h plus rh prime, and that's equal to 0. If we divide both sides by pi r, we have 2h plus rh prime and set that equal to 0. So in number 2, we're going to solve for rh prime and then substitute it back into number 1. So if we solve for rh prime, we subtract the 2h to make that negative 2h. So that's what that equals. And so now what we're going to do is we're going to substitute that into equation number 1. Okay, so we end up getting 2r plus h minus 2h, and that's equal to 0. And so we end up getting 2r minus h, which is equal to 0. And we want to solve for h. So if we solve for h, we get negative h, which is equal to negative 2r. And therefore h is going to equal 2r, which made it a lot easier solving this implicitly as we did in the previous example. And let me show you the previous example. In the previous example, what we've done, in order to solve for h, we plugged in the critical value to get that result for 2r. And so therefore, this solving implicitly gives us sort of a nice, better way of being able to solve when we want to solve for our critical number.